All right, hi everyone. It's a pleasure to be back. 特别关心你们请我去北京，来北京，谢谢。So I'm going to continue on in the vein of thinking about gauge fields and the bulk and quantum gravity. I'm in particular going to be interested in conjectural constraints on low-energy quantum gravity that follow from the consistency of actual non-perturbative quantum gravity, in particular insofar as how low-energy gravity is related to electromagnetism. So there are a set of standard conjectures about this kind of thing. So the oldest and perhaps the simplest is that whenever you have gravity coupled to electromagnetism, there must be states which are charged under the U1 gauge field. Doesn't have to be true in quantum field theory, certainly, but we think it should be true in gravity. There's a stronger conjecture, which is that not only must there be charged states, but we need states with all possible charges that are allowed by charge quantization. So again, that didn't necessarily have to be true. You can imagine electrodynamics with only even charged particles or something like that, but the idea is you can't have gravity like that. And then a more recent conjecture is that not only do you need to have charges, but at least some of them can't be too heavy. The idea here is that so if you have a particle, there has to be some particle whose charge in terms of the fundamental charge is nq, and then I want this charge to have a mass less than m Planck, for a reason I'll discuss in a sec. But then not only less than m Planck, but I want also this inequality to be obeyed. So essentially saying the mass is less than the charge in Planck units. This is a version of the weak gravity conjecture invented by these people. But in particular, the condition that the mass has to be less than the Planck mass is important because it ensures that this thing is not a black hole, right? So if black holes were allowed to be viewed as, having black holes obeying this is enough to obey the weak gravity conjecture, well, you see there's a less than or equal to sign here, and then the equal sign would be extremal black holes, and probably we think those exist. So for the conjecture to really, I think, be most interesting, this constraint is important to make sure that it's actually a particle. It's a thing you have to stick in your low-energy effective action. As I mentioned, I mean, none of these can be derived in perturbation theory, right? I mean, you can certainly write down a consistent perturbation theory that violates all three. In particular, this one, it's very easy to violate if you just hold the representations of the matter and the mass is fixed, and then you just take the gauge coupling to 0, make the coefficient of f squared large. But nonetheless, all three of them seem to be true in string theory, so maybe there's something to them. Now, in my opinion, the existing arguments for these are not totally compelling. I mean, there's something to the existing arguments, but for example, people sometimes you say, oh, well, obviously they're charged black holes. But if you don't have any charged particles, how do you make charged black holes? I mean, it's not. Maybe just nothing is charged, right? And even if there were charged black holes, I mean, why not only the even charges? I mean, a priori that doesn't seem like it would be inconsistent. For conjecture number 3, the original argument for why it should be true was that they said, well, otherwise there would be all these non-BPS charged black holes, extremal say, but non-BPS, that would be stable, and that would be weird. And I mean, it's true, it would be weird, but I mean, hopefully we can do better than that would be weird in saying why some version of this conjecture should be true. And actually, this conjecture, I mean, they weren't even really sure what the conjecture should be. They considered various options. The weakest one they settled on is where you don't even have this restriction that it has to be a particle. You just say some object whose mass is less than its charge in Planck units. I mean, and that one can be satisfied by black holes. So as I said, by itself, at least it seems less interesting, right? Because, well, probably then the extremal black holes will always satisfy it. So what should the conjecture be anyway? And I want to mention a nice recent series of papers by these people who are just studying, in terms of low energy, and studying many string examples, what kind of conjectures could be true. So in the remainder of this talk, though, I'm not just going to try and talk about, well, which ones empirically seem to be true in string theory. I mean, I want to understand if they're true, why are they true? What's the principle in quantum gravity? And I'm going to argue that, well, there's a paradox in ADS-CFT, which, at least the only way I can think of resolving the paradox, seems to require versions of all three of the conjectures. So my arguments for conjectures 1 and 2 are pretty general. For conjecture 3, I would say it's less strong. It depends on more details. And correspondingly, I'm not yet able to tell you exactly what version of the weak gravity conjecture should be true. So this is based on a paper from last year. There were some other related papers, one by Monica Guica and Dan Jafris, and then one that Hiroshi and I should hopefully be finishing soon. All right. Now, let's remember that in ADS-CFT, there's been a lot of work in the last 5 or 10 years about how do we talk about operators deep inside of the bulk directly in the conformal field theory as operators, viewing the correspondence really as an isomorphism of states. And so also Shidong will explain sort of the state of the art of this in his talk later this week. But just to sketch briefly, the idea is you have some bulk field here sitting in the middle of the bulk, and in the CFT you can represent it in some way like this, where this O is the operator which is dual to phi, and then there's a systematic way of generating the quantum corrections. This story also works when there are gauge fields in the bulk. You have to be a little more careful to make sure you talk only about gauge invariant operators. So here are some gauge invariant operators, right? Like this could be F mu nu here, a local gauge invariant operator, but then you can also have Wilson lines connecting to charge operators, Wilson lines going from the boundary to the boundary, closed Wilson lines between charges. These are all the kinds of operators that make sense in bulk electrodynamics and should make sense in the CFT. And actually, they do make sense in the CFT. So in particular, the gauge field is related to the current, to a U1 global symmetry current in the CFT in the usual way. And then the machinery, the standard machinery I mentioned in the previous slide, can more or less go through to represent all of these operators. It's worth commenting that you see this current here, right? So this current in the CFT is a global symmetry, but then you see in the bulk it's a gauge symmetry, which is consistent with the general idea that there shouldn't be bulk global symmetries. That was also mentioned at the end of the previous talk. So also in this paper with Hiroshi, we're going to, I think, give a better explanation of that, for example, that works also for discrete symmetries. Okay. So today, though, the thing I'm going to be especially interested in is reconstructing these operators, bulk operators in the CFT in this ADS Schwarzschild geometry. Geometry is a little more interesting than this one. The reason why it's more interesting is because now there's a new kind of gauge invariant operator. You can have this Wilson line here that starts on one boundary, goes through the wormhole, and ends on the other boundary. And well, the interesting thing is that this operator, this horizon threading Wilson line, can't be represented in the CFTs using the techniques I just mentioned. It can't be represented just using the global symmetry current in the CFT. So let's understand why not. Well, the issue is that as we learned from Juan, the Hilbert space of this system actually tensor factorizes, right? Because there's a CFT on the left and there's a CFT on the right. The Hilbert space is a tensor product of the two. And then the state is this thermal field double state here. Consider perturbations thereof. But, well, in a tensor product Hilbert space, any operator whatsoever is a sum of tensor product operators between the two sides. And those operators appearing on the two sides are separately gauge invariant. But with this Wilson line, well, if we try and cut it in the middle and represent this half in that CFT, and this half in that CFT, right? So that would be doing something like this. Well, we find that the pieces aren't separately gauge invariant. But since this by itself is not gauge invariant, it can't be an operator on the Hilbert space of the right CFT because all operators in the Hilbert space of the right CFT are gauge invariant. They're physical operators. So this prevents any attempt to make the parts separately out of the current, just using the currents in the left and right CFTs. So we can get more intuition for why this ran into a problem by just thinking very simple system, pure electrodynamics on a spatial R times S2, right? So that's the same as the topology of this slice here, R times S2. This is the R, and then there's the S2. So Well, the interesting thing is that we have this Gauss constraint, and so at least if we're doing pure QED, that means no charges, then if we integrate the electric flux through the sphere here, and we integrate the electric flux over here through some other sphere there, well, by Gauss's law, these two operators are going to be equal as quantum operators. So if you think about it in quantum field theory, maybe that's a little surprising. I mean, these are two macroscopically space-like separated operators which are equal in all physical states. So in particular, there's absolutely no way that the Hilbert space of this system could factorize, if I made a cut here, into some operator algebra on the left and some operator algebra on the right that are factors. Because if the Hilbert space tensor factorizes, right, the only operator in common between the two sides are multiples of the identity. Whereas this is a non-trivial operator. You can have flux going down the tube. So this apparent conflict with the CFT, right, because the Hilbert space doesn't factorize, but as we just discussed, the CFT factorizes, right? So there's some tension here, which I'll call the factorization problem, right? The bulk seems to not want to factorize because of the presence of these gauge constraints. But we know that the microscopic theory, the CFTs, does factorize into the two parts. Now, of course, the conclusion of this isn't going to be that ADS CFT is inconsistent and we should all go home, right? So, I mean, it's not really going to be a conflict, but we have to understand what it means. So we can start to get a sense of what it means by considering the algebra of this Wn, so that's this Wilson line and the charge n representation going across. We can study its algebra with the charges, the asymptotic charges in the left and the right. So you see that if I look at the commutator of W with Q left minus Q right, well, I get W on the other side, which means this W is a creation operator for 2n units of Q left minus Q right. So acting with this Wilson line, you're making the black hole a little bit Reisner-Nordström, or the wormhole a little bit Reisner-Nordström. You're threading some electric flux down the tube. In particular now, if you look at the expectation value of Q left minus Q right, in a state where you take the thermal field double and you act with this Wilson line operator, you get something non-zero, right? Because you get this flux going down. But then since we know, so far this would have been true even in the theory with no charges whatsoever, right? In the bulk, this equation would just be true. But now we use our microscopic knowledge from ADS CFT. We know that the Hilbert space factorizes into the left CFT and the right CFT. And then immediately we see that these charge operators, the charge operator in one copy of the CFT can't be zero, right? So this equation couldn't be true in a factorized Hilbert space if Q right and Q left acted on the separate factors and were both zero, right? So hey, we've already established conjecture number one, and we haven't even gone that far. So this means there have to be states with non-zero charge just in one copy of the CFT. All right. Now, once we've included these dynamical charges, the argument I gave before about integrating Gauss's law also isn't going to go through anymore because now del dot E isn't equal to zero. It's now equal to rho, and rho is a non-trivial operator. So that's good. So at least including the charges is going to help with that too. And indeed, I'm now going to argue that once we have the dynamical charges, this factorization problem really becomes a UV issue, right? So without the charges, we had this crazy thing where we had an operator here is equal to an operator there macroscopically far away. That's an IR, non-factorization. But I claim that once we have dynamical charges, this is really a UV, a question about the short distance properties of the theory. And I'll explain that more as we go on. Now, to make this precise, I'm going to explain it in 1 + 1 dimensional lattice gauge theory. And so this factorization problem in that context was studied in some nice papers by these people. Okay, so here's 1 + 1 dimensional lattice gauge theory. Hamiltonian lattice gauge theory, of course. Why would anyone ever do any other kind of lattice gauge theory? So here we have sites. On each site, I'm going to put a charge field. So like here's a charge scalar. And then on each link, there's an element of the gauge group, U1 in this case. So then the gauge transformations act on phi in the obvious way. So V is also an element of the group. Each site gets a gauge transformation. And then U on the link variables transform in this conjugate way under gauge transformations. And importantly, the boundary conditions will be that the gauge transformations are trivial at the ends, and just for something, we could put Dirichlet boundary conditions on the scalar. Now, the reason we like those boundary conditions on the gauge transformations is because then Wilson lines are allowed to end at the boundaries, right? So that's the same as in ADS-CFT. The standard quantization of the photon and the bulk allows the Wilson line to end on the boundary. So here we're mucking up the thermal field double here, right? This is like the left CFT and the right CFT. So there's this W, this Wilson line operator that just goes all the way down from one side to the other. And then we also can take the charge field, and then we can, for example, run the Wilson line to the right boundary, or we can take the charge field and then run the Wilson line to the left boundary. And either way, we get a gauge invariant operator. Now, because we're in 1 + 1 dimensions, we can actually just solve the Gauss constraint and write down closed form and the functional form of all gauge invariant states in the Hilbert space. They just look like this. So they're just functionals of W and phi left and phi right. Or we could even choose them all to be phi left or all to be phi right. I'm going to actually, since I'm interested in cutting the theory, what I'm going to do is I'm going to say in between site L and site L + 1, so everybody to the left of that I address to the left, and everybody to the right of that I address to the right with the Wilson line. So that's like trying to make it factorize as best I can. But actually it doesn't factorize, because you see this W is still here. We still have this Wilson line. It's going all the way down. And although we now have dynamical charges, still the Hilbert space doesn't factorize, right? So this W can't be generated by any pair of algebras, which are localized on the left and on the right. Just somehow we're still not able to cut this W. So introducing charges hasn't solved the problem for us, but I claim actually it's made it better. Why has it made it better? Well, the reason is that now we have a new operator which I'll call W prime. So here's a picture of W prime. So we start at the left, we run the Wilson line up to site L, and then we stick in a phi dagger. And then we put in a phi at L + 1, and then we keep running the Wilson line. And, well, the reason why that improved the situation is because this operator actually behaves identically to W in low energy correlation functions, right? So this is essentially some sort of gauge covariant version of the operator product expansion you see here, where you're allowed to replace a phi dagger phi by a Wilson link in between them. And so there was some nice paper by Abhijit recently discussing this kind of thing in more detail. All right, so with that in mind, now here's the proposal. Okay, so here's how we're going to represent W in the CFT. The idea is, well, here's some correlation function involving W, the Wilson line going through the wormhole. But I'm just going to cheat. I'm not going to put W there. Instead, I'm going to put this W prime, where I just run the Wilson line here for a while, and then I stick a charge, and then I stick the anti-charge, and then I keep going. Okay. And in low energy correlation functions, these will behave the same. But now you see this piece is gauge invariant in the left CFT, and this piece is gauge invariant in the right CFT, and so now I know how to represent this operator using the standard reconstruction machinery. Now let's make two immediate comments about this proposal. So first of all, in order to cut the Wilson line in the fundamental representation, we need a bulk field of charge 1, right? There's a Wilson line of charge 1. We want to cut it. We need a bulk field of charge 1. So there must be a state of charge 1, so that's conjecture number 2. So, which remember, conjecture number 2 is the complete popularization of the charge lattice. So there are states with all allowed charges, so we get them by acting with the operators we use to cut the Wilson line. Okay. Now, another interesting thing is that although you need these charges, they could be quite heavy, right? So I mean, these charged operators could be all the way up at the gut scale. And the ADS radius could be, much lower energy scale than that. But you see this Wilson line, well, you might have thought this Wilson line is a rather low energy operator. It's a low energy effective field theory operator. And certainly a bulk effective field theorist would talk about it without needing to discuss the effective action up at the gut scale. But what we've learned here is that if you want to represent that operator in the two CFTs, then you need to know about the charges, even if they're quite heavy. Okay? Now, this isn't an observable violation of bulk effective field theory, I should emphasize. So, of course, if you're living in the bulk, you just use bulk effective field theory and you can get by with just the gauge field. But if you're, perverse enough that you really want to describe everything you do as you go through life in the language of the CFTs, then you're going to have to know about these charges. And so this is a violation of something which is called effective conformal field theory, which is the idea that knowing the low dimension operators in the CFT is enough to know low energy bulk effective field theory. Here it's clearly not true. We need to know these high dimension charges to represent W. All right. So I view this as a nice, sharp manifestation of this general fact that IR questions in quantum gravity can be UV sensitive when there are black holes around. All right. Now, let's stop and think about what we really accomplished here. So here's what we figured out how to do. So you come to me, and you give me a low-energy correlation function. And then I give you an operator in the CFT, and I tell you you can use that one as your W. Okay? But then, but now say you change your mind, and you say, oh no, that wasn't actually the correlation function I was interested in. Actually, there's an extra operator I'm interested in, and I'm going to put it right in the center there. Well, you can catch me, right? Then you can see that I really had put those two little charges there, and that I'm not actually talking about the Wilson line. You caught me. I could try to fix that by bringing my two charged operators even closer together, but then you'll just catch me again by putting another operator in there, right? Okay? So to avoid this sort of infinite regress, what I need to do is I need to preemptively bring the operators together until one of the following things happens. So one option is that I just bring them together within the Planck scale. And then now in the bulk, okay, we don't really know what's going on. So at least I've now sort of postponed the problem as far as it can be postponed. I mean, you could say that's already a solution, since now, instead of a problem, we just have something we don't understand. Well, that could be the case, but well, something else that could happen, which would be easier to understand, would be that there's some larger length scale before we get to the Planck scale, where when I bring the operators together to within that length scale, the physics changes and stops being Maxwell. So either possibility we can describe by saying that the gauge field must be emergent. I'll be able to say more in the case where it's emergent within effective field theory, which is basically what this option is. The other option is it just emerges at the Planck scale. But at least within effective field theory, we'll be able to see more about how it works. So indeed, it's very helpful to have an example here so we can see how this kind of thing works in practice. So the example I'm going to use is this CPN-1 sigma model, usually studied in 1 + 1 dimensions. I'm going to study a D space-time dimensions. I keep doing that. All right. So here's the model just for people born after 1980. So you have n complex scalar fields, and then you impose a constraint that z dagger z equals 1. And then you also impose a gauge symmetry where you rotate all of the z's together by a phase. And then you impose a SUN flavor symmetry mixing amongst the z's. Okay. So in this theory, the Hilbert space factorizes. So this is a scalar field theory, I could have a lattice scalar field theory, and at each point in the lattice, I just have a particle moving on CPN-1. Okay, and then there are no constraints between the sites, so the Hilbert space will factorize site by site. But nonetheless, as you probably know, this model has a phase in any dimension where it flows to scalar electrodynamics in the infrared in the Coulomb phase. Well, actually, you have to be in 4 or higher to get the Coulomb phase. But anyway, and just to remind you, this is a model for the bulk. Okay, this is not a model for the CFT. All right, so now it'll be interesting to understand, okay, the Hilbert space factorizes, so how are we going to get Maxwell physics in the IR? That seems related to the factorization problem, right? Okay, so just to say one slide about how this model works. So here's the Lagrangian. So you have, it looks like a ordinary kinetic term for scalar electrodynamics, but now the gauge field is made out of the Z. So Z's are all there are. There isn't really a microscopic gauge field. Then the idea is that in any dimension you can solve this at large n. That was what was explained in the references. And what you do is you introduce a Lagrange multiplier sigma to enforce this constraint, z dagger z equals 1. And then you view this A as an auxiliary field whose equation of motion imposes this. So then that makes the action quadratic in the z's, so you can integrate them out and you get effective action for a, mu, and sigma, and at large n it's exact. Okay, so that's why you can solve the model. And now the key point is that by adjusting g, this coefficient, we can arrange for this sigma to get a VEV, which is non-zero, but which is light in units of the cutoff. And we can arrange also at the same time for SUN to be unbroken. All right. So in that phase, well, actually in any phase, but especially in that phase, we're interested in the quadratic term in the effective action, right? And what we find is that there's a Maxwell term with the non-zero coefficient, which means that there's a propagating gauge field. Well, at least in high enough dimensions. And so by doing the calculation, you find that these are the couplings that you get. Now, what we're really interested in here, though, is how is the existence of this IR equivalent phase consistent with the microscopic factorization of the Hilbert space in terms of the charge scalars? Well, the answer is not too hard to understand. So remember previously, this was how we made the gauge field out of the Z's. But to really understand the factorization, we need the lattice version of this equation so that we can really see what's going on. So here's the lattice version. So the Wilson link, U, so say this is going from site X to site X plus delta. Delta is the lattice displacement vector. We see what happened. I mean, this is the formula. You have a Z dagger on X and a Z on X plus delta. So this indeed transforms as a Wilson link. But then the key thing is this is precisely this gauge covariant OPE, right? So now the Wilson line is I just string a bunch of these together, and then I can make a cut down the middle, and I get back to, and then this is just the charge, right? So if I cut here, then look, here's a Z dagger and here's a Z. So it's precisely this OPE I was doing before, but now it's exact, right? So that's all the Wilson line is it's made out of bringing these charges together. So things work as expected. Now, let me just finish by going back to the weak gravity conjecture and saying what this model has to say about the weak gravity conjecture. So you see the masses and charges of everything are now computable quantities in terms of the UV parameters. So we could imagine testing the weak gravity conjecture in this model. So here's the thing we would want to be true. So we have charge 1, so we can just put the gauge coupling here. So now to do this, I mean, there's a G here, so we're going to have to bring in gravity somehow, right? Otherwise, we're not going to test the weak gravity conjecture. At least it'll be trivially true. But you see, well, to solve the factorization problem, we need to take the cutoff of the model to be less than the Planck scale. If we didn't do that, then we didn't solve the problem, right? Then we're just back to having the non-factorization. The charges aren't helping us. And then to have the strongest test, we should take the cutoff of the model on the Planck scale to be comparable. Okay. Now in doing this, we have to be careful about some of the things Malcolm mentioned, right? So there are many light fields. Newton's constant gets renormalized. It looks like that. For simplicity, I'll just do d greater than 4. Here was what from the CPN model, what we found the coefficient of the Maxwell term would be. And well, seemingly miraculously, if we combine to get the weak gravity conjecture, which said that m squared g is less than q squared, well, from these we just see that q squared over g is lambda squared. So the weak gravity conjecture just says that the masses of the charges are light and cutoff units, which is true. That's the whole point of the model, that that's true. Otherwise, we wouldn't be describing it wouldn't have a quantum field theory description at all. So apparently CPN automatically obeys the weak gravity conjecture. Now, why is that true? The logic is actually quite simple. So in order to solve the factorization problem, right, we needed to have this energy scale where the Maxwell term in the effective action has 0 coefficient. Okay, that was to get rid of the Gauss constraint in the UV. So that's infinitely strong gauge coupling in the UV. To get a weak gauge coupling at low energies, we need to generate a large coefficient for the Maxwell term by running the renormalization group and integrating out the Z's. But if all of the charges are heavy, that's no good, right? Because then they won't run in the loop. So in order to generate a big Maxwell term, we need light charges, right? And that's the whole point of the weak gravity conjecture. Weak gauge coupling requires a light charge field. Okay, and this can be generalized to multiple U1s in some nice way that Hiroshi and I will explain. All right, so last slide, promise. So what we've learned is that the fact that the CFT Hilbert space factorizes, despite the geometric connection through the bulk, is really telling us powerful information about UV short distance physics in the bulk, right? You know, ADS-CFT is a UV complete theory of quantum gravity, so we can ask, what does it tell us? What kind of UV cutoff does it give us on bulk effective field theory? Apparently, it has to be the kind which is consistent with these conjectures 1 through 3. then the fact that we can describe this Wilson line despite the factorization, I would say, is an important check of the idea that the wormhole exists at all, right? So that's this idea that the space-time can be connected through the bulk, or if you like, the geometry can be emergent, even though the CFTs are unconnected. So then just to relate to the previous talk, right, so these charges from which the gauge field emerges, they regulate these edge modes of Donnelly Wall, or what were called soft hair on the horizon in the talk we just heard. And the gravitational cousins of these guys recently appeared in a paper I put out a couple weeks ago explaining the Rutak-Yanagi formula in CFT language. So they're really related to many things that we like. And finally, I should end by saying there's a gravitational version of the factorization problem too. Obviously, it's also a gauge theory. There's a Hamiltonian constraint. So resolving that is going to require UV information about quantum gravity. But what are the things that the graviton emerges from? I mean, that is a much harder thing to answer. All right, so I think that's it. 谢谢大家。